All right, so let's get this party started. So we are going to continue with solutions a little bit. And one of the things about solutions is this concept of an electrolyte. So an electrolyte is basically a solution that will conduct electricity. And the best candidate for creating an electrolytic solution is by just simply dissolving an ionic compound in a solution. So, for instance, sodium chloride is an ionic compound. Sodium chloride will dissolve in water and split apart and give you the sodium plus one cation, the chloride minus one anion. And in doing so, in that water, it will now conduct electricity. Another example of an ionic compound is calcium nitrate. Notice here that calcium nitrate dissolves, don't let this throw you off, the fact that we have two nitrates for every one calcium cation. And the reason we do that is the calcium is a +2 and each of the nitrates is a -1. Excuse me, means that when it ionizes or dissolves, we are going to get two particles of the nitrate ion and only one particle of the calcium ion. So again, this would also conduct electricity. Along these lines, if I were just to take plain old sugar or sucrose and dissolve sugar in water, sugar actually is not an ionic compound. If I dissolve that in water, sugar AQ, actually this will not conduct electricity. So it's it would be a non-electrolytic solution. So a problem that we can do with electrolytic solutions, or simply put, it has nothing to do with the fact that it conducts electricity. A problem we can do with this sort of dissolving process looks like this. So what is the concentration of the nitrate ion? So question mark molar concentration of the nitrate ion, given that the concentration of the salt, the calcium nitrate we dissolved, is 0.230 molar. And most people will look at that and they're like, well, if for every one of these, one of the compound we're going to dissolve gives two nitrates, I'm guessing that molar concentration is 0.460 molar, or 2 times the 0.230. So, and you'd be right. But we can actually show our work this way, where we've talked about using the stoichiometric coefficients from a balanced equation to go ahead and make a stoichiometric ratio, and that's exactly what we're going to do here. If you make your first term what's dissolved, and your next term the fact that you get 2 moles of NO3 for every 1 mole of CaNO3 that you dissolve, notice that actually moles of the compound, moles of the salt, calcium nitrate will cancel. We're left with moles of the nitrate per liter of solution, which actually is molarity. So yes, we were right the first time with regard to just inspecting it and coming up with the right answer, but you need to be able to do something like this. So it's just like another stoichiometric calculation is the way I think of it, using the balanced relationship when something dissolves. So this will be due on Monday. Problem 13.79. Okay, so we're going to work a problem here in a minute, and it is actually going to give us mass percent. And we talked about mass percent earlier in the course. We talked about how you calculate it, but once you've calculated, you can unpack mass percent as this. It is actually the grams of the component per 100 grams of the mixture. And we said actually solution is just another example of a mixture that's a homogeneous mixture. Okay, and the beauty of mass percent is that since it doesn't deal with any volumes, then actually it is, the volume is what gets us with regard to changing when the temperature changes. So this mass percent will not change with changing temperature. So let's work a problem. And I can't remember how, let's see if I can kind of make my little picture up here. This problem, it says that I am going to dissolve 46.87 grams of isopropyl alcohol. Sometimes I actually kind of shorten that into IOH, isopropyl alcohol. And I'm going to dissolve it in enough solution to give my final solution volume 300 milliliters of solution. There's no question there yet. We could actually answer a few questions. We can knock out the molarity. So in this case, my target question mark is moles of IOH per liter of solution. So the strategy for this one is we're going to have to take the grams of IOH, go to moles of IOH using the molar mass. And then once we have then we can use that and divide those moles by that volume. So this is 300 milliliters of solution. A follow-up question is, we actually cannot knock out the mass percent of isopropyl with the information we're given. And then here it says, it's kind of a silly way to ask it, but if I'm giving density of the solution is 0.975 grams of solution per 1 milliliter of solution. If I'm given that, then I can go ahead and knock out the mass percent, and I'll show you what that looks like. So for the first one, we need to come up with the molar mass of isopropyl alcohol. So that would be 3 times the decimal number for carbon, 12.01, plus 8 times the decimal number for hydrogen, because we have 7 hydrogen here and 1 hydrogen here. So that's 8 hydrogens. So 8 times 1.008. We have 1 oxygen, so we take 1 times the decimal number for oxygen, 16.00. And you're looking at a molar mass of 60.09 grams per mole. And as I've been saying, you need to be able to think of that as 60.09 grams of IOH per 1 mole of IOH, isopropyl alcohol. So let's go ahead and see what we have. In this particular instance, I would simply take the raw mass I was given of the isopropyl alcohol and divide it by the solution volume. Because my target here is, like I said, moles per liter, okay, of solution. And this is grams per milliliter of solution, so actually I have to fix both the numerator and the denominator. So if I fix the numerator first, this was the molar mass that we came up with for isopropyl alcohol. Notice that if I want grams to cancel of isopropyl alcohol and I want to be left with moles of isopropyl alcohol, I need to use the flipped version of the molar mass. Now if I stop now, I've got moles of isopropyl alcohol per milliliter of solution. So I can't stop now. I need to fix my denominator. And to fix my denominator, I introduce one more term, 1,000 milliliters of solution over 1 liter of solution. So milliliters of solution cancel. We're left with moles of isopropyl alcohol per liter of solution, which is perfect. That is molarity. One last look at how we're going to round this. And it looks like I have 4 sig figs here, 3 sig figs here, 4 sig figs here. So I need to round according to 3 sig figs. And it looks like this. Okay, what I probably would call this, by the way, is just simply 2.60 molar isopropyl alcohol. So the original question said, can we come up with the mass percent of isopropyl alcohol? And no, you couldn't with just the information given the original problem. But if we throw one more piece of information here, which is the density, then actually we can go ahead and work the problem. So the density is 0.975 grams of solution now. Now remember, that's not isopropyl alcohol, that's grams of solution per 1 milliliter of solution. Basically, if we're after mass percent, if we think of what that is, mass percent is we need to get to the grams of IOH, which actually was given in the problem, divided by the grams of solution, and that will give us mass fraction times 100%. That will give us parts per 100. So we've got this, right? So we just need to know grams of solution. And we can actually get to grams of solution if we know the density and the volume of the solution. And we know the volume of the solution was 300 milliliters. So it looks something like this. Again, if we go back to the raw information that was given, we have 46.87 grams of the isopropyl alcohol dissolved or made up into 300 milliliters of solution. So I need to get that milliliters of solution into grams of solution. And do you see how I can do that? Dun, 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 dun. Okay, but I want, looks like I'm going to use the flip of that, aren't I? So if I just go ahead and introduce density here, the inverse of density, the milliliters of solution will cancel, and we'll have units of grams of solution in the denominator. Now you're going to see me on my slides kind of do this stepwise, but if I would go ahead and introduce one more term here, times 100%, I would be done. But I'm going to go ahead and divide this out. Looks like I'm allowed 3 sig figs, so you're looking at, this is a mass fraction, of 0.160 grams of isopropyl alcohol per gram of solution. Simply to get that into parts per 100, we simply multiply by 100 or 100%. So your weight percent isopropyl alcohol is 16.0% by mass. Very good. So these will also be due on Monday. Chapter 13, problem 107, Chapter 13, problem 113. So these get kind of fun, solution concentration problems. Okay, so one of the last topics I want to talk about with regard to solutions is, well, I guess it's not the last. But there is this thing where you prepare a stock solution. I'll go ahead and make my little, this is what we call a volumetric flask. It's got one little mark. It's very precise, relatively precise with regard to the volume it contains. So basically you prepare something that's relatively concentrated, and then you take some of this and you add it. Hi, come on in. Yeah, I am. Go ahead and grab your notes. And you add it to, you take some of this and you transfer a certain amount. And after you transfer it, then you add water to dilute that back up. So this is your stock solution, and this is what we call your diluted solution. Well, why, if this is our target, some sort of diluted solution was what we wanted in the first place, why didn't we go right for the diluted solution? And the answer is we get more accuracy if we make something basically stronger, more concentrated first. And then we go ahead and dilute from there, because we measure a certain mass and dilute it up. And then we take some of this and we transfer and we dilute it up. Sometimes it's called serial dilutions. We actually will take this and make one more dilution or more dilutions, each time getting more and more dilute. So we're going to take a look at how we work these problems of knowing, or different sorts of problems we can know by working this. Actually, I have a little video to show you. Hopefully it'll work. I don't know. You can tell kind of how concentrated something is by, in this case, if it has a color. The video we watched didn't have a color. But you can see, you'll see it's kind of a diluted color. Notice they're using a pipette like we saw before. So, and the word is aliquot. It's, I think, a French word for saying a certain amount of kind of subliquid. So he transfers it over, he or she lets it go, lets it rip in this new volumetric flask, and then dilutes it up to volume. So again, you can tell by the just intensity of the color that this is the one on the left is what we call the stock, and the one on the right is the diluted. So this is just kind of another look at it. The caption of this actually goes along with creating a 5 liters of solution, and that's a lot of solution. So actually, the odds of getting a 5 liter volumetric flask, I don't have one, but I've got a 1 liter. So anyway, they say that if your target is, and we'll be talking a little bit, well, we talked about making the solution in the first place. No, we'll talk about these numbers. How do you get, how the dilution numbers work out? So I'm going to make a couple of, maybe I'll make it on the board, I think now. So working these problems, I like to make a picture so that I can kind of see what's going on. So I always go, the thing on the left is my stock solution and the thing on the right is my diluted solution. So this is more concentrated, this is less concentrated. These are both volumetric flasks. It says that 25 milliliters of a 0.16 molar calcium chloride solution are transferred. So I'm going to go for my stock and I'm going to transfer 25.0 milliliters, 25.0 milliliters of this. And then down here, I'm going to say what that concentration was. I'm going to say it was 0.160 molar calcium chloride. And I'll go ahead and unpack what that means. The big M means molar. So that means I have 0.160 moles of calcium chloride in 1 liter of solution for my stock. And this is why I like to draw a picture, because I'm like, I can see that. So then it goes on to say that those 25 milliliters were transferred to a different volumetric flask, and I added water to bring up the new volume of 125 milliliters. This is my diluted solution. And the question is, what is the molarity of the diluted solution? So in this case, I'm actually going to work a few problems to knock it out. I know that I can use the molarity and the volume to see how many moles of calcium chloride that were transferred. And then all I got to do is take those moles that were transferred and divide it by 125 milliliters. That's my solution volume. So let's see how that works. So like I said, I kind of think of this as tracking the moles, to kind of two connected problems. The first problem is to come up with to use molarity and volume to come up with the moles that were transferred. And then the second problem is to take those moles that were transferred and divide it by my solution volume. So it looks like this. So the moles of calcium chloride that were transferred. Now the problem is we've run into this before with this sort of problem. If we want to go from volume using molarity to get to moles, if our volume is in milliliters and our molarity is in moles per liter, we have to convert our milliliters to liters first. And we know that there's 1,000 milliliters in 1 liter. So if I introduce a term here, 1 liter of 1,000 milliliters, milliliters will cancel, I'm left with liters of solution. Then I can go ahead and knock in my molarity. Okay, so we said the stock was 0.160 moles of calcium chloride per 1 liter of solution. There we go. The unit-wise, milliliters of solution have canceled. Liters of solution have now canceled. We're left with moles of the calcium chloride, which is what I wanted to do for the next part. So it looks like we need to round according to 3 sig figs. You're looking at a nice neat number, 0.00400 moles of calcium chloride that were transferred. So like I was saying then, the last step is to take this number of moles and divide it by my new solution volume. Excuse me. And it looks like this. Where again I have the issue of I have the milliliter problem. Okay, because molarity is moles per liter, not moles per milliliter. So I can introduce one more term to clean that up. 1,000 milliliters over 1 liter of solution. So units of milliliters have canceled. I have moles of calcium chloride per liter of solution. Looks like I missed a 0 in my figure here, 125.0 milliliters. But it looks like we're allowed 3 significant figures because of those trailing zeros after the decimal. So you're looking at 0.0320 moles of calcium chloride per 1 liter of solution. And as I've said before, I probably just use the letter M for molarity. We'd say it's 0.0320 molar calcium chloride. So it never hurts to double check your problem. Does it seem reasonable? So I came up with a 0.320 molar. Oh, sorry, 0.0. That wouldn't make sense. 0.320. So yeah, that seems reasonable that it diluted that much. So, all right, so let's do another problem. Different picture here. I think I'll just go ahead and do this picture here. Again, left to right, I know it's going to be a dilution problem. I know we're going to have some sort of stock solution, and I know we're going to have some sort of diluted solution, but you're going to see that the solute has changed, and kind of what we're after has changed. So in this problem, it says how many milliliters. So actually, I'm going to transfer a certain amount of volume. So question mark milliliters. Do we need to transfer? And it gives me 1.35 molar is what my stock is. And then it says that over here, my diluted, I want it to be 500 milliliters, or 3 sig figs, of diluted solution. And my target molarity is given 0.275 molar. So again, we're after something a little bit different. Now we have the molarity of the diluted solution, and we're after how much of the stock do I need to transfer. It's a very practical, I know it's hard for folks who haven't been around a lab to know how practical that question is, but it definitely is a practical question. So in this problem, we're going to kind of reverse engineer it. Notice that since I have the volume and the molarity of my diluted solution, I can get to moles of sodium chloride. If I can get to moles of sodium chloride, then now I can actually use and these have to come, these moles, they have to come from my stock. So now I can use the moles and the molarity to get to volume, okay? So again, we kind of had two sort of connected problems that we've talked about, of the type we've talked about before, that to work the one single problem. So like I said, in this case, I'm going to kind of start on my diluted side and knock out the moles of sodium chloride I have swimming around in here, and know that they had to come from this volume, and know now I can use moles and molarity to get to volume. So over here, I was on the product side. Over here in my diluted solution, I know I have 500 milliliters and I know it's molarity. If I start with my 500 milliliters again, well, a few things. I've been telling y'all, if you see a big M like that, know what it means. Know that that big M next to the 0.275 means 0.275 molar, which is moles of calcium chloride per 1 liter of solution. Now, if you keep that in mind, you can use it as, I say, kind of a puzzle piece to work the problem. So the fact that I have units of liters in the denominator of my puzzle piece means that if I'm starting out with milliliters, I have to get to liters first. And I can do that by remembering that there are 1,000 milliliters in 1 liter. So now units of milliliters cancel, I have units of liters. Now actually I'm ready to go ahead and bring in my molarity, and my units of liters will cancel, and I'll have units of moles, which is awesome. So milliliters have canceled, liters have canceled, and I have moles of the solute, which is kind of the first step in working this problem. Looks like we're allowed 3 digits, 3 significant figures. So you're looking at the number of moles that were transferred were 0.138 moles. And again, all of those moles had to come from this aliquot, this volume, and they came from this molarity. So now we have molarity, moles, and we're after volume. So I would start with these moles, the 0.138 moles of NaCl. And remember, and I'll just do it on the board here, when we unpack that M, what does that mean? That means moles per 1 liter. So 1.35 moles of NaCl per 1 liter of solution. All right, so knowing that, can you see where I'm going to have to flip this? Because I want moles to cancel. Okay, so it looks like this. I put, this is from the molarity, 1 liter of solution over 1.35 moles. So now moles cancel, but if I'm after milliliters, I'd have volume in liters, but not yet in milliliters. So I have to, it's the milliliter-liter problem. So if I recognize there are 1,000 milliliters in 1 liter, then you've gone from units of liters to milliliters. So moles of NaCl have canceled. Liters of solution have canceled. We're left with units of milliliters of solution, which is perfect. Looks like 3 significant figures, 3 digits, and you're looking at 102 milliliters, which would be kind of a difficult aliquot to get, but it's not impossible. And, you know, I've been saying, well, does that seem reasonable? And I have no idea. I just have to hope I did my calculations. All right. So we transfer 102 milliliters of this stock solution, dilute it up to 500 milliliters, and this is our new concentration. So this is just like a little heads up. If you do kind of wander into the text of this book, it will talk about M1V1 is equal to M2V2, and that's kind of a common way to work these, but in my general chemistry class that I teach, General Chemistry 1 and General Chemistry 2, they can't do that until General Chemistry 2, so neither can you. You need to do it as I've done it here. So these will also be due on Monday. Getting close to our last Monday.
So is there something else to do on Monday?
Yeah, everything, we finished this part now, so.
Like 13.107 and 13.113.